Okay, so we're going to continue on this packet that I gave you on Friday, okay? So if you would find it, that would be great. There might be one of you that doesn't have it, and if that's true, there's one extra. I think Mackenzie, it might be you, Mackenzie, good if you don't have it, I'm not sure. Or maybe I just made an extra. Anyway, so for those of you that weren't here on Friday, we went through the whole first page, talked about different terms, mechanical waves, electromagnetic waves, which are based on the type of material through which they move. Mechanical needs matter, electromagnetic don't. And then based on how the wave moves, there are also three different types. One are called transverse, one are called longitudinal, and the other surface. And then towards the end of the class, we were looking at the different features of a wave. And so transverse waves are really the ones that you're used to seeing. A transverse wave looks like this, where this flat line here is what we would call the rest or equilibrium position. It's what the medium would look like if there was no wave moving through it. Okay, but then, so we talked about the fact that this part is known as the crest, the highest maximum point of positive displacement, and the lowest or negative displacement is called the trough. Okay, now what I didn't say to you, this is a transverse wave. What I didn't point out to you was in a longitudinal. Remember, the longitudinal were the ones that had the molecules close together and then separated, and then close together and then separated. And it's because if you push something in, they move all the molecules close together. So like in a normal medium, the rest would look like this. So they'd all be equal spaced apart. But then something comes along and it pushes like this row in, makes these close together, then it backs off, which spaces them apart. And then it pushes in, and then it backs off. So you get these. What I didn't tell you on Friday was, instead of crests and troughs, for a longitudinal wave, the ones that are pushed together are called compressions, which should make sense. Compressing something. And the ones that are spread out are a word you probably haven't heard before. They're called rarefactions. Okay? So maybe tonight you might want to see if you can work the word rarefaction into a sentence, because it's not one that we would often say. But in a longitudinal wave, it just parallels the trough in a transverse wave. Okay, we also talked about the wavelength, the length of one wave. Has to include a full crest and a full trough, but it doesn't matter if you measure from the beginning of a crest to the beginning of a next crest, or from the middle of a trough to the middle of a trough. As long as you have one full cycle, then it's considered a full wave. One full cycle. Okay? And then the last piece we talked about, right before the bell, was the height or the depth of the wave. And whether it's height or depth, it's called amplitude. The amplitude of the wave. And it's simply the distance from the rest position to the maximum positive displacement or the maximum negative displacement. But what does the amplitude tell us about the wave? Well, the amplitude, if you think of a water wave with more amplitude, it means it's higher, would have more energy. So the amplitude tells us about the energy the wave is carrying. It's true whether it's a sound wave or a water wave or a wave in a slinky, right? If I increase the amplitude of the wave, it just gets bigger. If I decrease the amplitude of the wave, then it means it gets a lower energy. So the amplitude tells us about how much energy the wave is carrying. If you happen to be in the ocean and you get hit by a wave with a huge amplitude, you'll know that it's energy that it's carrying because it'll really hit you. Whereas if it's just gentle little tiny waves, not a lot of energy. So water waves, then you could feel the increase in amplitude. But what about sound waves? The greater the amplitude, the greater the what? I'm pausing to let you think about it for a second. And it's the loudness. The amplitude of a sound wave is the loudness. And on your sheet of notes, right here, we're at the top of, oh yeah, and for those of you not here on Friday, the second page is in the wrong way. So you have to flip it over, and you're going to need to re-hole punch it because the hole's on the wrong side. So this should be the top of the front of the second page where it says the amplitude of the wave tells us about the energy. Okay, so sound waves, the greater the amplitude, the louder the sound. In light waves, the greater the amplitude, the what? What do you think amplitude has to do with light wave? I'm pausing again so you can think about it. And what it is brightness. The greater the amplitude of a light wave, the brighter the light. Okay, now something that non-physics people tend to get confused on is that one can't speed up a wave by adding more amplitude. Like if I shout at someone, it doesn't make the wave travel faster, it just means it gets there with more energy, right? And the same with water. If you fill your bathtub and you're tapping your finger in it as you sit on the bathroom floor, you tap harder and harder, the amplitude, the height of the wave gets bigger, but it doesn't travel any faster. So the amount of energy a wave is carrying doesn't change its speed, it just changes the height that it gets to. Like, so if you think a wave in a ball game, the amplitude would be how fast, how high you jump up, how excited you are because my Maple Leafs are winning. Oh wait, they lost. It's not how quickly the wave moves around the stadium through the medium. Okay, so you can't speed up a wave by adding energy. Adding energy just changes the amplitude only. And we'll come back to that in a few minutes when we get down to speed. But before that, we need to talk about period and frequency. And this was really where we were on Friday. Okay, you've heard the word period a ton of times in your life. The period of anything is just how long it takes to go through one full cycle. So like if you think of the pendulum that we were doing in the last unit, right? You pull the pendulum back and let it go. It swings down. It swings all the way up to the other side. And then it swings all the way back. And when it gets back to where you let it go, that's one full cycle. So you could time it, and you could find the time it took to do that. If you're sitting out in Killarney Lake in a canoe, you could time how long it took one wave to pass you by. You might actually want to time a whole bunch of waves. So you might discover that like 10 waves pass in 30 seconds or something. So you could find the time for one wave if you did this, right? If 10 waves go in 30 seconds, then one wave would go in 3 seconds. And so the period would be 3 seconds. So period, it's at the time for one complete cycle. So because it's a time, it's a capital T. And what did we just do here to get the 3 seconds? We took the 30, the total time, and we divided it by how many waves. So the formula for period is the total time that's passed divided by the number of cycles that have occurred. So this is the equation for period of a wave. Now there's something that's really closely related to period. It's called, so period is a capital T. It's called frequency. Oops, it really is an EQ. Frequency. And it's a small f. And frequency is like how many waves go by in a certain period of time. Well, from our little experiment on Killarney Lake, we can also get the frequency. How many waves go by in a certain period of time? Frequency is then just equal to the number of cycles over the time. So for our frequency here would be 1/3, right? It would be 10 waves over 30 seconds. The 10 doesn't have any unit on it. Here it would have been 30 seconds over 10, and we would get 3 seconds for our period. But here it's 10 over 30, so we get 1/3, and the unit would be 1/seconds. And we don't tend to use that unit. Instead, we rename it, and we call it a hertz. And I know you would have heard of hertz